Hello world is what this outputs, and this is a factorial function. What's going on here? Who came up with this? Hello, it's me. I'm the one who came up with that. So, today I want to show you an esoteric programming language which I invented. It's called Funciton. Yes, the spelling is a bit weird. It's a typo for function, get it? If you already know what an esoteric programming language is, then feel free to skip ahead to 3 minutes 12. Now, since you clicked on my video, you probably know what a programming language is, and you've probably heard of more than one of them. You may have heard of Python, C#, JavaScript. These are some very normal and common programming languages. You may have heard of some more uncommon ones, like for example Haskell, which is a functional programming language, or Lisp, which is a list processing language. But there is one thing that still unites all of these programming languages, the normal and the weird, and that is that they're all aiming to be a serious programming language to write serious programs in. So you might think, yeah, well, obviously, like, why would you not be serious about writing programs? Well, see, there are 3 possible reasons that someone might invent a programming language that is not serious. Reason number 1, minimalism. By that, I mean minimalism of the instruction set. So some people want to invent programming languages in order to prove that you can do a lot with very few instructions built in. And when I say do a lot, I mean Turing completeness. There is this concept in theoretical computer science called Turing completeness. Now, you don't need to know the details about all of this, but suffice it to say that all of the normal programming languages that you know, and even some of the weird ones, are Turing complete, which means that they can perform all computations and calculations that you would expect a program to be able to do. So the point in minimalism is to try and create a programming language that allows you to do all of that, all possible computations and calculations, with only very few instructions. Another reason someone might want to invent an esoteric programming language is to come up with an odd syntax. And by odd here, I mean unusual, out of the ordinary. Most programming languages look kind of similar. Like, even the very different ones still seem to have like some kind of common elements or common structure. The idea in an esoteric programming language with an odd syntax is to make it appear at first sight that there is something unusual about this. Maybe it doesn't even look like a programming language. The third reason someone might want to make an esoteric programming language is to make it as difficult as possible to program in. So when I say difficult, I don't just mean that they want to do difficult programming tasks in it, but that the language itself is so difficult to program in that even simple things take a long time or a lot of effort. The esoteric programming language that I'm going to show to you today, Funciton, does the first 2. So it has only very few built-in operations. We're going to get to that. And with regards to the syntax, well, you've already seen the factorial function, which is this. So let me walk you through how the factorial function works so that you can get an idea of what the syntax is. But before I start, I want to point out that this is not an image, this is not a graphic, this is in fact a text file. Each of these boxes are composed of Unicode characters. Here's a small sample of Unicode characters that I used by Funciton syntax. As you can see, these are the box drawing characters which allow me to draw boxes and lines. Now, obviously, those characters are not going to be on your keyboard. Some people memorize numerical old codes to type these. I don't do that. I actually use a program called Unikey, which I wrote myself, but it only works in Windows. It only works with the US keyboard layout, so be warned. So you'll be seeing me type codes in the editor, such as this, for example, and as you can see, my characters get replaced with box drawing characters. So this is how I'm going to be entering the code. The first thing you might have noticed is that one of the boxes, namely this box here, is very different from the others. The others all have a double line on the right and the bottom, and this one has double lines on the left and right. And then, of course, there are these boxes here, which have double lines on all 4 sides. So this one here, I call the declaration box. This one defines that there is this function called exclamation point, and the fact that there is one line coming out of it defines that it has one argument or one parameter. So one input. After that, this line sort of splits into two, as you can see. So this value that goes into the function is split into two copies. So this is the same as just using a variable name twice in a function. Now, one of these two, namely this one here, the one that's going to the right, will hit this greater than sign. And on the other side of that greater than sign, we have the number 2. So what we want to do is we want to check if the number is either 0 or 1. And if so, the result is 1, because 0 factorial is 1 and 1 factorial is 1. Now you might legitimately wonder why a greater than sign then, because we want n less than 2. Well, the reason for that is that the arguments to the greater than function go in counterclockwise order, starting from where the output goes. The output is at the bottom, which means that the 2 is actually the first argument. So we're not checking n less than 2 or n greater than 2, we're checking 2 greater than n, which is the same as n less than 2. Alright, with that out of the way, the result of that goes down this wire and into this question mark. Now, I'm sure you've already guessed that the question mark is like an if then else. So if n is less than 2, then the result is 1. So again, we go in counterclockwise order. So we have if this, then this, else, all of that. And then of course the line at the bottom, which just stops in the middle of nowhere, that is the output of the function. Whatever comes out of there, that is what the function will return. So let's take a look at the else branch, because what we want to do to actually calculate the factorial is we want to multiply the number that we got with the factorial of 1 less than it. So in other words, n factorial is the same as n times n minus 1 factorial. So you can see that this line here, which contains our original n, gets split up into 2 copies again. One of those 2 copies goes right here into this multiplication box, and the other one goes into this. And this is a musical flat symbol, which is what I decided to use for a decrement function. So this will take the integer and reduce it by 1. So we'll turn 7 into 6, 6 into 5, etc. And then we call the exclamation point function again, which is the factorial function. So that's the same function that we're declaring. So this will be a recursive call, but because we've decremented this and eventually this number will reach 1 or 0, we will eventually satisfy this condition with the less than 2. So that's why the recursion stops. So you can see that the decremented value goes into the factorial function. The result of that goes into the multiplication, which is what we want. And then that gets pumped into the else branch for the if. So I hope that you'll agree with me that this is relatively straightforward, that if you understand what factorial is, then you can understand how this code works. But here's the twist. None of these boxes are built-ins. Every single one of these boxes calls a function which is itself written in Funciton. So that begs the obvious question, what actually is built-in? Like, how do you build something like a decrement function out of even more basic pieces? Let's go into detail on that. Here are the 6 built-ins that Funciton actually provides you with. Number 1, standard input. So in other words, you can read input that the user provides to the program. And this is fairly normal in all programming languages. So how do you do standard input in Funciton? The answer is very simple. We're going to draw a box which is double lined on all sides. And we're going to have a line coming off the bottom, like this. It doesn't have to be the bottom, by the way. It can come off in any direction. This is just my convention that I have the output of the program usually point down. So this program will take input and then immediately output that same input. To give you an example, I'm just going to create this very simple file here containing a single character, the digit 1. And then I'm going to invoke my program with that input, and you will see that it will actually output the same number, the number 1. So now that we know how to do standard input, let's see if we can actually run our factorial function that we already have on the number that we put in. So I'm going to draw a function invocation box right here, which we'll call the factorial function with the input. Now let's see what happens if I run this program. Whoa, I get an error message. What is going on here? Well, you can see that it mentions UTF-32, so clearly this has something to do with Unicode. Well, a programming language wouldn't be very useful if it could only ever output numbers, right? So of course Funciton needs a way to output strings, or Unicode text. So what's actually going on here is that the input file, which consists of the character number 1, is going to be interpreted as its Unicode value, which happens to be 49. So what this program ended up doing is it ended up calculating the factorial of 49. Now 49 factorial is a pretty large number, and if you try to interpret that number as a Unicode string, well, it's just not going to work, because many of the bits are just not going to be valid Unicode characters. Now I'm not going to go into detail in this video on how the string encoding works, but I'm going to just show you the names of the functions that I use to convert between integers and strings. First of all, we need a function that takes a string from the input, which is in our case just the number 1, but as a Unicode character, and converts it to a number, in this case the actual number 1. That function is called that. After calculating the factorial, we need to turn the result of it back into a string. In other words, so for example, if the answer is 1, as it is for 1 factorial, we need to turn that back into the Unicode value 49, which is, the character 1. So we're going to use the opposite of this, which looks like that. Now, if I run the same program, hopefully we get the number 1. And if I change my input file to contain, for example, a 47, then we're actually going to get 47 factorial, which is a pretty large number. Number 2, function invocation. Now technically you've already seen this, right? We've just invoked the factorial function, as well as the functions that I've already written, which convert between integers and strings. And of course you've seen the factorial function itself invoke, for example, the multiplication function, or invoke itself recursively. So this function invocation can be recursive. Number 3, bitwise NAND. Whoa, those are some big words. What's going on here? Buckle up, this is going to get technical. Let's start with something that may already be familiar to you because it's common in all of the serious programming languages. Bitwise AND, which is usually written with the ampersand character. So for example, imagine you have the numbers 3, let's say, and 6. Let's see what happens when we bitwise AND that. Now bitwise, obviously bit stands for binary digit, so let's look at these numbers in binary. Now 3 in binary is 1, 1, but of course because computers operate with bigger numbers, there will be leading zeros. So let's put some leading zeros there. I'm just gonna pretend that we're gonna deal with bytes here, so I'm just gonna use 8 bits at a time. Now the number 6 in binary is 0, 0, 0, 1, 1, 0. Now, in order to calculate the result of a bitwise AND, we're going to look at each bit position separately. So we're going to look at these 2 bits, and then we're going to look at these 2 bits, and this is why it's called bitwise. Now the result of a bitwise AND is going to have a 1 in every place where both of the inputs are 1. So in our first place we have a 1 and a 0. They're not both 1, so that's going to give us a 0. In the second place we have 2 1s, so that's actually going to give us a 1. And then in the next place we have a 0 and a 1. That's not both 1s, so that's a 0. And then everything else is just 2 zeros, so everything else is just going to turn out 0. So the result of 3 and 6 is equal to 2. Now just for completeness, I'm going to show you bitwise OR as well, which in most programming languages is written with a pipe character like this. So let's take a copy of this stuff here, and let's see what OR is. Now the result of an OR operation is 1 whenever any one of the input bits is 1. So let's take a look at the least significant bits. We have a 1 and a 0. And there is a 1 among them, so the result is going to have a 1 there. Then we have 2 1s. Well, we don't care that there are 2 as long as there is a 1 in there. So the result here is 1. And then we have another 1 and a 0. So again, the result is 1. but the remaining bits, they all have 2 zeros, so there aren't any 1s in there. So the result is 000000111, which happens to be 7. Okay, but when I talked about the Funciton operations, I said NAND, not AND. So what's going on here? Well, there is one more bitwise operation, which is bitwise NOT, which operates on only one number at a time. So let's see what the bitwise NOT of 6 is. In most programming languages, it is written with a tilde character. So let's take the binary form of that number. Now, the bitwise NOT of a number is 1 whenever the input is 0, and 0 whenever it's 1. So it's the opposite. So every 0 turns into a 1, and every 1 turns into a 0. So you end up with this result. If you were to convert this from binary, you'd get a relatively large number. In this case, you would get 249. But integers in computers tend to be signed, which means that they can express negative numbers as well. So usually the highest bit is actually a sign bit, and when that bit is 1, the number is negative. So in this case, we actually get a negative number. Now, when all of the bits are 1, instead of 255, which is what it'd be if it were a byte, we say that this is -1, because this is 1 less than 0, which has all zeros. And then from there, we can just count down the binary. So 11110 would be -2. And then this would be -3, and so on. So what we end up getting here is actually -7. Okay, so what about this then? I said NAND. What does NAND mean? Well, NAND is actually AND followed by NOT. So it's like NOT AND. So in other words, if we have, for example, the 3 and the 6, if we were to bitwise AND them and then NOT them together, in any serious programming language, this kind of syntax would generally be used, right? But in Funciton, this is a single operation that can only do NAND. So to give just an example, if we wanted to take 3 and 6 and we wanted to calculate the NAND, that would be the same as doing the AND, which we've already done, and then applying NOT. In other words, invert all of the bits. So in this case, the result would be -3. Now, why the heck is this useful? Why are you rambling on about this esoteric bitwise operation? Well, there is something very special about NAND and also NOR, but in Funciton I decided to go with NAND, so we're going to focus on NAND. You see, if your programming language only has an AND operation, then you would not be able to do OR by just using AND in creative ways. It can't be done. But with NAND, surprisingly, it is actually possible. Before I show you how to do OR, I'm going to show you how to do NOT using only NAND. So let's say we have some random binary number like this one here. What we want is we want the bitwise NOT. So we want a number where all of the zeros become 1s and all of the 1s become zeros. But the only operation that we're allowed to use is NAND. Well, let's take a quick look at what happens if I NAND the number with itself. Well, the first thing that we do is AND. So let's see what this looks like if we apply AND to the number AND itself. Well, if you remember, whenever we have 2 1s, the result is going to be a 1. So this is going to be a 1. And whenever we have 2 zeros, because they're not both 1s, the result is going to be 0. So since both of the bits are always the same, it's always going to be, well, zeros turn into 0 and 1s turn into 1s. So it turns out that you end up getting the exact same number again when you AND a number with itself. But remember that we're actually doing NAND, which means that after the AND operation, we also get a bitwise NOT, which gives us the result that we want. So, ta-da! We can actually do bitwise NOT simply by NANDing a number with itself. To write this out in a concise equation, we can say that A NAND A is equal to NOT A. So that begs the question then, how do you do the other bitwise operation? How do you do bitwise AND, bitwise OR, and maybe bitwise XOR, which I haven't even mentioned yet? Well, let's get to that. So first, let's take a look at AND. We already know how to do bitwise NOT by just NANDing a number with itself. Now, since NAND is basically the same as doing AND followed by a bitwise NOT, what we want to do is we want to cancel out that bitwise NOT, which we can actually do by just doing another bitwise NOT. So A and some number B, let's say we have numbers A and B and we want to AND them together, is actually the same as NOT A NAND B. And then of course we know how to do the NOT. We've got a formula right here. So all we need to do is just do the NAND and then NAND that with itself. And ta-da, we have a formula for AND. Now, OR is going to be a little bit more interesting. In order to do OR using only NAND, I'm going to use something that is known as De Morgan's laws. Now, De Morgan's laws allow us to turn ANDs into ORs and ORs into ANDs using NOTs. De Morgan's law for OR is that A OR B is actually the same as NOT, open parenthesis, not A and not B. You can verify this for yourself by just going through all possible combinations of zeros and ones for A and B. There are only 4 combinations, and you'll see that this checks out. Now, we know that doing an AND operation and then NOTing the result of that is the same as NAND. So we can just get rid of this and write NAND here. Okay? And now the only thing we're left with is bitwise NOT. Well, we know how to do that. We just NAND this with itself. So this is just A NAND A, and this should just be B NAND B. And ta-da, we end up with a formula for OR. Now you may reasonably ask, how do I actually do NAND in Funciton syntax? Because there's like no function that you can call, because it's a built-in. It's not a function invocation. So I'm going to write a quick program which does nothing but NAND on 2 numbers. So we're going to start by creating these boxes here, one for the number 3 and one for the number 6. So we already know that the result of that was -3, I think it was. But let's verify if that's actually the case. Maybe I made a mistake. So here's how you do NAND. You take these wires that come out of the number boxes and basically smash them onto one another. So the 2 parallel lines, if they are both inputs, which in this case they are, inputs to the T-junction, then this will calculate a NAND. So this program would calculate 3 NAND 6, but as we've seen before, it will then try to interpret that as a Unicode string, which won't work. So we're going to have to add another function invocation to the function that converts that to a string, which looks like this. So if I try to run this program now, I expect to see the result of 3 NAND 6. I get -3. So now that we know how to compose NOT, AND, and OR out of just NAND, let's see if we can turn those into actual Funciton function declarations. So I want to declare a function that will do the bitwise NOT. Let's start with that. The first thing we need is the declaration box, and it needs to have a connector, a single connector because it has only one input. And we need the value duplicated because we want to NAND it with itself. So let's create a splitter. So now we have 2 copies of the value. And now we want to NAND the values with one another. So we just connect the 2 values. And it forms this neat little box. And there we have it. That is a bitwise NOT function. So this is what a program would look like that would use bitwise NOT on a number. I'm doing the same conversion from strings to integers as before, but besides that, the only function call here is NOT, which is the declaration that we've seen earlier. So let's see what happens if I call this on a number such as, for example, 5, let's say. And we get -6, which is what we expect. The bitwise NOT of 0 is of course -1. And if I put -1, I should get 0. Indeed I do. Okay, let's move on to AND. Now, unlike the NOT function, the AND function has 2 inputs. So I'm going to have those inputs go left and right. Okay, now let's look at the formula for AND. Well, we need to do the NAND first. So we need to combine the A and the B using the NAND T-junction. And then after that, we need to do the bitwise NOT. Now, I could do the bitwise NOT by calling the function that we declared earlier, but you've seen that doing a bitwise NOT is actually very simple. So I'm actually just going to write it out, and I'm going to do that in all of my code. I don't really need the bitwise NOT to be a separate function. So here we have a simple program that we'll just call the AND function on the numbers 3 and 6. And I'm just going to turn that into a string. And then let's see what that outputs. Now, earlier we calculated what 3 and 6 is. It was 2. So let's see if that is what we get. And indeed we get a 2. Now let's see how to do the OR function. Now in the case of the OR function, we need to do the bitwise NOT on the inputs first. Now I'm going to put this little box in the clipboard because it's going to be easier that way. And I can literally just insert it right here and right here. And ta-da! Suddenly we have an OR function. So here's a program that would calculate 3 or 6. Now we've seen earlier that the result of that should be 7. And indeed that is what we get. Now there is one more common bitwise operation that I haven't mentioned yet, but I'm going to mention it now. And that's XOR, also known as exclusive OR. Now XOR works quite similar to OR. If you have zeros, the result is 0. If you have a single 1, then the result is 1. And of course, if you have a 0 and then a 1, the result is still 1. But if you have 2 1s, this is where it's different. So if you have 2 1s, the result goes back to 0. This is why it's called exclusive OR, because it excludes the case where there are 2 1s, and it turns that back into 0. How do we express that using only NAND? Well, this formula is slightly more involved. Let's see in which cases we actually get a 1. Well, we get a 1 whenever A is a 1, but B is 0. That's the same as saying A and not B. And the other case where we get a 1 is when A is 0 and B is 1. Let's see if we can write that in Funciton. So let's start with the declaration box as usual. So the first thing that we're going to do is this first parenthesis. We're going to do A and not B. So we're going to have to use a bitwise NOT on B, which is the second input. So that's our NOT B. And now in order to do an AND on both of those, the A and the B, we're going to have to do a NAND followed by a bitwise NOT. So let's do that. So this is what the first parenthesis would look like. But now in order to do the second parenthesis, we're going to need to take copies of those values A and B. So we're going to need to draw some T-junctions to do that. So first, let's draw a T-junction right here. And let's actually take this wire all the way around the top of the function declaration. For the other one, we can put a T-junction right here. Okay, so in our first case, it is this variable here that we did the bitwise NOT on. In the other parenthesis, we need the first variable to be knotted. So we're just going to put that little box here. And now we need to AND those together, which we can do just by NANDing them and then negating the result. Okay, so now we've done each of the two parentheses. We've done this bit and we've done this bit. And these are the results of each of those. And now we need to do the OR. Now how do we do OR? Well, let's look at the formula for OR. In order to do OR, we first need to bitwise NOT both of the inputs and then do an AND. Now, if you look very closely at what we've done here, you'll notice there is a bitwise NOT here and there is a bitwise NOT here. So there is really no point in bitwise NOTing it a second time. Instead, we can just eliminate those so that those will cancel out. And then all that's left to do is a NAND. And there you have it, XOR. So here's the same program from earlier, but this time with the XOR function plugged in. So we're going to calculate 3 XOR 6. Now 3 in binary is of course 1 1 as we've seen before, and 6 is 1 1 0. So if we XOR those two, what do we expect to see? Well, we expect the 0 and the 1 to become a 1. We expect the other 0 and 1 to become a 1. But the double 1 is supposed to be 0, and then the rest of course is 0 because the inputs are all 0. So the result would be 5. Let's see if our program actually outputs 5. Let's run it, and it says 5. Ta-da! Number 4, bit shifting. Imagine you have some binary number, which in this case is 25. So bit shift means that we're shifting the bits either left or right. So let's start with left. So in most programming languages, we would write it as 2 less than characters. So 25 shift left 1 would mean that we're shifting all of the bits to the left by 1, and then we're adding an extra 0 at the end. Now, the effect of this is the same as going times 2, so this would result in 50. So in other words, if you go shift left n, which would mean that you're shifting left by n number of bits, then that is actually the same as multiplying it by 2 to the power of n. Similarly, shift right is when we shift the bits to the right, as the name implies. So 25 shift right 1, for example, would result in a bit pattern like this, with the last bit chopped off and then extra zeros added at the start. So this would result in the number 12. So this is kind of like dividing by 2, but we always round down. So this is the same as going 25 divided by 2 to the power of n, if we shift right by n, except rounded down. Now let's pad these to 8 bits, because I want to show you what happens with negative numbers. Remember that I said that if you have all of the bits set, including the sign bit, then your number is actually -1. So let's take a look at this number here, which would be -25. If we were to shift the bits left by 1, we would get this number here. Remember, we always add a 0 bit at the end. Then the number we end up getting is -50. So once again, it's effectively the same as multiplying by 2. But let's take a look at what happens if we shift right. We end up with this number. You'll notice that I've added an extra 1 at the start rather than a 0. So whenever the number is negative, we're actually shifting in 1 bits in order to keep the number negative and not treat it like some very large number. Now in this case, the result is -13. If we were to take the -25 and divide by 2, we would get -12.5, and we are rounding down. So from -12.5 rounding down, we get -13. Number 5, less than. Now, this seems very simple. You just take two numbers, a and b, and if a is less than b, you return true, and if not, you return false. Now, what do I mean by true and false? Well, in Funciton, true is actually represented by the number -1, and false is represented by 0. In many other programming languages, true is represented by 1. Now, why would I use -1? Well, again, if we look at this in binary, you can think of this as a ton of 1 bits and this as a ton of 0 bits. So now if we were to take a bitwise not of a true value, we actually get false. If we were to use the number 1, then the bit pattern would look like this. And then if you try to bitwise negate this, you would actually get -2. Which is kind of not helpful. It also means that we can use the bitwise operations like OR and AND that we've discussed earlier to treat true and false as Boolean values. So how do we write bit shift and less than in Funciton syntax? We've already seen that the bitwise NAND operation uses a T-junction. What else can we do with single lines and box drawing characters? The answer is we can draw a cross. Something like this, perhaps. Now let's pass in some values here. Let's use the same numbers that we used before, 3 and 6. So we end up with something like this. Now, this one piece of syntax will calculate both the bit shift and the less than at the same time. So at the bottom of this cross, we're going to get the bit shift. In this case, this would calculate 6 shift left 3. And on the right-hand side here, we would get the less than, which in this case would calculate if 6 is less than 3, which is false, so we get a 0. Let's see what happens if we run this as a standalone program. Well, we get an error message. Cannot have more than one program output. Well, that's understandable, because if the program outputs multiple values, which one is it supposed to output? Or if all of them, then in what order? The programmer needs to be explicit about these things. So Funciton only allows one output, and we need to tell it what to do with that. So let's do two things. First, I'm going to convert all of these integers into strings, like this. And now let's just concatenate those two strings so we just get one after the other. I'm just using a library function for string concatenation here. Alright, so let's see what we expect this to output. Well, I said that the bottom output of the cross thing will do the shift, and the right side here will do the less than. But because function arguments are always in counterclockwise order, it means that this one here is going to be the first argument to the string concatenation. So we're going to see that one first. And we expect 6 less than 3, we expect that to be 0, and we expect 6 shift left 3, which is the same as 6 times 2 to the 3, which is 6 times 8, which is 48. So I expect to see 0, 4, 8. Let's see if that's what we get, and it turns out that is exactly what we get. Just for completeness, I'm just going to swap the two numbers 3 and 6 and show you that it does exactly what I said it would. So now we expect the bit shifting operation to calculate 3 shift left 6, which is going to be 3 times 64, which is 192. And we expect the less than operation to calculate 3 less than 6, which is true, so -1. So I expect to see -1192. And indeed, that is what we get. And finally, if you want to do shift right instead of shift left, then all you need to do is just pass in a negative number here. So let's change this to a -1, and let's see what the program outputs now. And as you can see, we get the 0 because 3 is not less than -1, and the 1 because 3 shift right 1 is 1. So this is all nice and fine for when we want to calculate both a shift left and a less than with the same inputs. But that's going to be very rare, right? Most of the time you only want one or the other. So let's see what happens if I do just one of the two. So I'm just going to remove quite a fair bit of the code here. So this should calculate 3 shift left 6, right? Well, if I run this program, we'll see that we get the same error that we had earlier. We can't have more than one program output. So we need a way to get rid of that. Now, we could get rid of it by, for example, NANDing it with 0, which will always give you -1, and then you can, do something with that. But there is actually a trick that we can use to just nullify an output. And this is what it looks like. Now you might think, oh wait, this is another built-in that you haven't told us about. But actually it's really not, because it's kind of a NAND operation, but also it's like connected to itself, which means that it doesn't have an output, and so the interpreter will never try to evaluate it. So you could argue that this is a NAND operation that is just never calculated. But for our purposes, this is exactly what we want. We want a construct that doesn't have an output, so the interpreter doesn't try to evaluate it. Now if I try to run this program, you will see that the output is indeed 192, like we expected for 3 shift left 6. Now we could, if we wanted to, always use that weird loop, but we could also just define ourselves a shift left function that we can just use more conveniently from now on, because we can always invoke functions. And here's what such a function would look like. So you can see that it has the same cross and it has the same construct. I mean, it's upside down here. I'm just demonstrating that that is the same thing. And the output of this function is, of course, the part of the cross operator that gives us the shift left. We can, of course, put the construct on the other line instead in order to make ourselves a less than function. And that would look like this. Now, if you're wondering why I'm bending this line downwards, this is actually important because the orientation of the inputs, the A and the B that goes into the function, is relative to the orientation of the output. So you cannot have an output point in the same direction that one of the inputs does. It would have to point either up or down, and I'm making it point down in order to maintain my convention that the arguments are always in counterclockwise order. And finally, number 6. Well, I'm actually not going to cover what number 6 is in this video. I'm going to cover it later. But that's because we don't need it yet. Now you might reasonably ask, how are you ever gonna do anything useful with these 5 super simple, super basic functions? And you're quite right, they're a little limiting, but it turns out that these are enough for the programming language to be Turing complete, which means that we could write an addition function, a function that takes 2 numbers and returns the sum. You should definitely have a crack at this. Think about how to write an addition function using only these 5 building blocks. Now take a quick look back at the factorial function. Just as a quick heads up, you are going to need this function in order to do addition as well. So start by thinking about how to implement an if-then-else function using only these 5 basic operations. And then once you have that, see if you can come up with an addition function. And I'll see you in the next video.